not the definition is important if you select. This is as users, I speak, not as a developers. I would say that the screens are developed mostly in Korea, produced in China, developed in Korea, in South Korea, and in South Korea. South Korea, the best are, I'll speak maybe later about this. These are Samsung and LG. Sony also produced in Korea, or they make them in China. The last information is that the development of new screens is done in South Korea, but the fabrication is also in China. So Asia is the best developer and producer of good screens, of displays. So the most important characteristic is the resolution, or so-called DPI, dots per inch, or PPI, pixel per inch. This is the number of pixels per unit surface. This is important. So this is one characteristic which is the same for all screens. I mean, doesn't matter what the dimension of the screen is, what the diagonal they measure is. According to the resolution, you can have an idea what the quality of the screen is. Okay, the example is 300 dots per inch. That means that we have 300 rows, 300 columns, and 90,000 pixels per inch, per square inch. Why we continue with inches? This is the influence of the states again. We know that we have a system C, international system for all measures, but they still impose us, it's very strange, inch. You see, this is the inch. They still measure with steps, with feet, etc. But you know the dimension, 2.54 centimeters. So the important to notice, that's why I start with this for the screens. The high definition provides better quality on a smaller screen. The resolution is the criterion for quality of the image. The first, we started with the cathode ray tube. When I was a child, I watched TV on this screen, so-called CRT. It was the basis, this cathode ray tube was the basis of the first TV sets, television sets, and of the first computers, and also oscilloscopes. The oscilloscopes, and a long time we used them for oscilloscopes, this principle. That's why they were so heavy, big. Yeah, the dimension and the weight was great. So it was, what does it represent? Just again, as history, a tube coated with phosphorus in inner surface, in the internal surface. And the electrons were produced by electronic gun when they came in contact with the phosphorus surface, the light produced by virtue of which we can see. It was disadvantages. They were very large, big, emit. It is by that time, again, some commercial in the optics, some publicity. These displays, they were dangerous for the eyes because they emitted electromagnetic fields. fields, just one, no more than one field. And also there was emission of small amount of X-ray band radiation. There were other problems. It was necessary to refresh the screen because of the phosphorus, and this constant refreshing resulted in headache sometimes if a long time we stayed in front of this display. They were heavy, I explained, but what is, again, commercial? Even nowadays, if you go in the optics to buy new glasses, and they offer you, okay, this one reflection, so, and this is protection. It is protection if you work in front of the computer. These glasses, they will protect your eyes from the displays that we are using now. Usually they are based on light emitting diodes. It could be new OLED, organic LED, etc., but they're based on LED. There is no more emission. There no problem at all. The problem, this is practical for you, are programmers, are informatikers. The problem with the eyes is when we watch the screen a long time. This is not that the screen influences us, but this is our problem. When we watch, we don't close the eyes. We just stare on the screen, and that's why the eyes are sometimes dry. And we should remember and exercise a little bit, even if we don't have time to make a break, just close your eyes to allow them to have more humidity. The next displays that appeared were the plasma displays. Some people, even nowadays, they say, I will watch my plasma. They don't exist more. They are no more used. It was the first flat screens. The technology PDP, plasma display panel, was based on the emission of light through excitation of a gas. It should be excited until the plasma state. The screens used small cells containing electrically charged ionized gases, which are plasmas. You can see some, okay, they were thinner, not like nowadays screens, but still thinner. You can see the construction of the plasma display with phosphor coating in the plasma cells, the display electrodes. We had the electrodes, and it's the principal. The address electrode we had, the vertical are display electrodes, the address are horizontal. This is the principle in the memories, by the way. If you know the physical construction of the memories. So, okay, we have rear plate glass, a dielectric layer, and front plate glass. The two glasses, between these two glasses is created the plasma, is the gas. The gas that was used in these plasma screens, plasma displays, was a mixture of argon, 90% of argon, and xenon. I'm not sure it's pronounced correct. I pronounce it correctly in English, but you understand, I think. So each pixel corresponded to one cell. This gas is contained in these cells. The cells are addressed. I don't think you can, I'm not sure you can see the pointer. They are addressed by row electrodes, and the column electrode from the other side, and between two electrodes, there was voltage applied, the electric field, and the gas was excited until plasma state. How was obtained the image? By modulating the value of the voltage applied between the electrodes and the frequency of the excitation. So modulation of the value of the voltage and the frequency. So it was possible to define 256 luminous intensity value. The colors were produced as usually with RGB, red, green, blue. In plasma displays, there was still some radiation. I told you that there is no radiation nowadays with LEDs, with light emitting diodes. But the plasma display also, there was some ultraviolet light radiation. Okay, this is the construction of the plasma display. I told you there are the electric glass layers from both from the inner and external side, the front plate glass, the rear one. They were coated by magnesium oxide. Here you can see the electrodes, the address electrodes, the horizontal, and the display electrodes, making from both sides the matrix. The plasma cells, they were coated by this RGB, made one pixel with, of course, these cells were filled by gas, this mixture of argon and xenon. So the color we obtained thanks to the blue, green, and red phosphors distributed on cells. Thanks to this phosphorus, the ultraviolet light is converted into visible light. And this made possible to obtain pixels, each one composed by 3 cells. They claim there were 16 million colors. If we ask painter how many colors there are, I don't think the painter will agree with the 16 million colors. I don't know how they measure them, but maybe they measure the intensity and the intensity of different combinations of red, green, and blue. The advantage of the plasma display was that the technology made it possible to obtain very big screens, large screens, with very good contrast. But they were expensive, very expensive, and the power consumption was very high, more than 30 times more than this one of the LCD. I didn't speak of liquid crystals. It was I have also one small movie on this, the difference of both. So in 2014, I underline this, in 2014, their fabrication was discontinued. They are no more fabricated. Someone can say, I watch my plasma at home, but maybe it is a plasma made before 2014. Liquid crystal display, so-called LCD technology. It was based on a screen composed of 2 parallel transparent transparent, as it was the case with liquid crystals as well, transparent grooved plates oriented at 90 degrees. See the plates and the orientation. Between these plates, there was a thin layer of liquid containing specific molecules, so-called liquid crystals. These crystals, they have different orientation when electric current is applied. See, depending on this orientation, combined with a light source, so the first straight plate acts as a polarizing filter, allowing to pass only the light components whose oscillation is parallel to the growths. The same principle as it was in, of course, this is the light, the orientation. There is a kind of matrix between both plates. When there is no voltage applied, the light is blocked by the second plate, acting as a perpendicular polarizing filter. So we have like two filters. When voltage is applied, the crystals will progressively align in the direction of the electric field and thus be able to pass through the second plate. You can understand that there is no much microelectronics here. This is mostly physics. Just electrical field is controlling the liquid crystals. And what I had to say from the beginning, that microelectronics is both interdisciplinary and multidisciplinary. It is interdisciplinary because it involves physics, chemistry. These are the basics, how it works, and to improve performance in nanotechnologies that obtain. This is engineering. This is engineering, the whole principle of electrical linked to electricity, of course. But it is at the same time multidisciplinary. It is multidisciplinary because the applications are multidisciplinary. We will see if we have time. We have time. The Internet of Things, there is communication, but communication, what is in communication? Also microelectronics. The basic is, yeah, high frequency. It is multidisciplinary. It is embedded systems. This is programming plus microelectronics. All computer sciences, yes, it is great to be programmer, but what can you program? Can you program on the page with the pen? Without software experts, we are not able to design our integrated circuits, because with these milliards of transistors, the principle of the design nowadays is also very close to maybe based on programming in C and C++, because we have also libraries, we have libraries with components with IPs, so-called IPs, intellectual products. Otherwise, it is impossible. So it is also multidisciplinary. And I switch to some other topics in order not to be so boring with pure techniques. For example, one of my PhD students now works for Bosch software. In the Bosch is making nowadays software for the electronic cars. But they ask, he studied electronics, but they ask people able to program, but to understand what they're programming, to understand the electronics inside. So it is multidisciplinary, and nowadays the world is multidisciplinary. Again, some examples of the liquid crystals. Usually they were used for the screens of the electronic watches. So each pixel was controlled by a transistor. The response time, thanks to it, was very short, between 8 and 10 milliseconds. I explained already that one pixel is composed by 3 subpixels, red, green, and blue. And how we obtain these so-called 16 millions of colors? By changing the electrical power that was sent to each subpixel, controlled by the transistor behind. Here is the microelectronics, the control of these of the molecules of the liquid crystals, and the color shades were affected by this electrical field. They also had disadvantages. With the time, they lost brightness, and the response times was slower. When the temperature was low enough. In high temperature, they were very temperature dependence. Thermal dependency was very high. In high temperature, the contrast was lost. So, and the refresh, you notice they didn't refresh very quickly the screen. The applications, nowadays, I think that most of them are replaced by LEDs, but for example, what you can see on the bottom right, you can't imagine that it could be the control system of a power plant. Who will replace the screens of this control system? This is absolutely. So in these systems, maybe they're still using LCD or the displays that existed by the time of the creation of this control room. But we can change our TV, our televisions, the TV sets. We can change the screens. Usually the new screens are on the new computers, but these applications, the most important applications and with high responsibility, they don't change them there. So calculators, watches, clocks, telephones by that time, not now. These are applications that are very, very easily changeable. Aircraft cockpit display, for example. Who will change this display? Only when they produce the new aircrafts. Otherwise, it is not something very important. Okay, microelectronics. There are so many things. I changed the topic very many times, but there are so many important things to be done. We speak about high technologies. High technology, we speak about nanometers, but these technologies, they are useful for information technologies, mostly applications. For computers, in the case of domestic applications, for example, we can and we still use controllers on old technologies. Why do we need very fast control of our washing machine or on the dishwashing machine or on the oven? for these applications, the technologies on level of micrometers is absolutely enough. And it is a waste of time to make a waste of time and money to use these new technologies. And mostly in the case, of course, FPGA can be used. In this case, they don't use FPGA because they have a lot of customers. FPGA are used in less applications, I would say. So, what is the difference? No. In this mode, I can't, okay, so it will be this way. But I have to share the screen in a different mode, display. And share the sound, okay. I hope the students understand Russian as well, yeah? Yes. Oh, non, merci.
Долгое время именно плазменные и жидкокристаллические телевизоры были главными конкурентами. Объясним, в чем суть каждой из этих технологий. Экран плазменного телевизора представляет собой стеклянную колбу из множества ячеек, заполненных газом. В нее вмонтирована своеобразная сетка из электрических проводников. При подаче электричества газ превращается в плазму. Она-то и вызывает свечение флуоресцирующих элементов на внешней стороне ячеек. Картинка состоит из тысяч таких крошечных кинескопов. Всеми элементами управляет процессор, который подбирает цвет свечения каждой ячейки, то есть пикселя. Таким образом создаются изображения. В ЖК-телевизорах экран многослойный с подсветкой. Тонкий слой жидкокристаллического материала расположен между поляризационными фильтрами. Работа такого дисплея, по сути, лишь изменение светопроницаемости кристаллической матрицы. Ячейки, субпикселы, наполненные жидкими кристаллами, меняют свою прозрачность при прохождении через них света. Этой прозрачностью можно управлять, добиваясь яркости экрана, а используя цветные фильтры, получать на нем разноцветную картинку.
Сейчас мы с вами плазменный телевизор на рынке практически не найдем. В чем же преимущество именно жидкокристаллической технологии? Во-первых, эти телевизоры обладают пониженным энергопотреблением по сравнению с плазменными. Плазменные телевизоры достаточно сильно грелись, у них было очень высокое энергопотребление. И одним из недостатков плазменных телевизоров было то, что специфика вывода изображения на экран подразумевала, что телевизор мерцает постоянно. У жидкокристаллических телевизоров таких проблем нет. И еще один недостаток плазменных телевизоров был тот, что они выгорали со временем.
В наши дни главная борьба между производителями телевизоров высокой четкости развернулась в первую очередь за толщину экрана, ведь это стиль, удобство и экономия пространства в помещении. Сегодня счет в этой борьбе за стройность экранов идет уже на миллиметры. Японские разработчики установили рекорд. Они создали ЖК-монитор толщиной всего 4,9 мм. Даже обычный смартфон сегодня толще. Этот экран можно вешать на стену как картину. Занимать он будет ничуть не больше места. Современные телевизоры потеряли в толщине и в весе, но приобрели огромный набор новых возможностей. Самое главное, что качество их изображений возросло многократно. Если первые экраны высокой четкости, так называемые Full HD телевизоры, выдавали картинку в 5 раз лучше по сравнению с кинескопом, то новейший формат 4К повышает качество Full HD изображения еще в 4 раза.
Я вернусь на моего PowerPoint, чтобы продолжить. Как видите, это тоже реклама. У них всегда это так и получается, что Ну, в YouTube очень трудно найти, может быть, в конце, если будет время, я покажу один фильм, который есть у меня очень коротенький, как это производство интегральных схем. Ну, это небольших схем, там, где студенты могут работать во Франции, у них есть такая лаборатория для обучения. Ну, это не реклама уже, это научный, как скажем так, образовательный фильм. So I'll continue with the touch screens because yeah, this is the next step that we have in lycée sur écran. I don't know, nowadays they're even, and they're very proud of it, that even the screen of the computer can be touch screen. So if there is a keyboard and mouse, there is no much reason to, and touchpad as well, the touchpad. The touch screen and touchpad, the principles are similar, but with the screen, it is much more complicated because the touch screen is the touchpad, there is no problem with the visibility, and behind there is only the sensoring effect that is used. In the screen, we have behind also the some image that is presented on the screen, and we'll see what are the differences. There are two types of touch screens. Why? Oh. Okay. The origin, in principle, there are two types: resistive touch screens and capacitive. In 1953, they started with first capacitive sensors. Then there were first infrared screens, 60, 72. The first resistive screen appeared in 71, but it is still used in a lot of navigation systems. You still have this resistive screen with the pen, controlled with the pen. In 84, because all these screens, the first touch screens, were only one point was identified where the coordinates of the point where the touching was done. Bell Labs in 84 developed the first multi-touch screen, something that we know very well, and how we can to enlarge or to change the image, the dimension of the images on the screen. So you can see the touchscreen combines computer peripherals by bringing together the display features of a screen and a pointing device. You can see how they mount them on the left side, and the image on the right side, how they look inside of the what is the construction. The resistive principle, in this case, we have two conductive layers separated by an insulator. In this case, we have insulating spacer dots, and the two conductive layers, here and here, these layers are on both sides. And on the top, we have some flexible, hard-coated outer membrane. And behind this is the substrate, the glass substrate usually. So the user applies pressure on one point, and creates contacts. On two sides of the screen, they are on the peripherals. There is the electronics that identifies the coordinates of the point where this pressure was applied. Okay, different applications. They are, in fact, they have the same application, but the screens, computer screens usually are capacitive. The capacitive ili ambijonkasne technology what you can see on the left, the principle, we have electrodes on four on these sides. We have a glass substrate, conductive layer, and protective coating. What is the principle in these touchscreens using capacitive technology? A uniform current flows through the surface of the screen. The user, when it touches, withdraws part of the current. So the principle is just the opposite of the principle of resistive. In resistive technology, we create contact electrical. In this case, we withdraw part of the current. The contact point is calculated according to the current value at the four corners of the screen. The value of the current in these points. You can see, can you imagine how complicated the algorithms are of this calculation and how precise should be this device? So external terminals, all the touchpads, iPhone uses them, and nowadays I think that almost all touch screens are based on capacitive technology. I will show you. So I don't know. I hope I worked a long time to find useful movies that give you impression, because just some presentations, when the lectures are live, we can show something, we can test something, I can show some screen and test how they work and not, but to make a little bit more interesting this lecture, and to have more demonstrations, I selected some movies which I can't show here. Should go and show. I hope it's not very long, this one. A new sharing. With sound. Okay. No.
Всем привет! Современные смартфоны или планшеты – это в большинстве своем квадратные экраны с парой-тройкой кнопок. Роль устройства для ввода информации полностью берет на себя тач-панель или сенсорный дисплей. Но как он работает и чем отличаются одни тачи от других и что лучше? Давайте разберемся вместе. Поехали! Сенсорных дисплеев в природе существует огромное множество. Они используются в промышленности, в терминалах оплаты, банкоматах, смартфонах, графических планшетах и еще очень много где. Сами тач-панели бывают резистивными, матричными, емкостными, проекционно-емкостными. Есть сенсорные экраны на поверхностно-акустических волнах, инфракрасные, оптические, тензометрические и индукционные. И в разных сферах жизни применяют разные сенсоры, при этом как принципы их работы, так и чувствительность, и тем более долговечность одних от других может очень сильно отличаться. Но у меня тут не научный канал, и я не хочу забивать вам голову ненужными подробностями, поэтому остановимся на самой сути. На данный момент самыми распространенными сенсорными экранами являются емкостные и резистивные. Раньше еще применяли инфракрасные, но в силу непрактичности их больше не используют. Чтобы не путаться между ними и сразу определять на ощупь, кто из них кто, достаточно знать одно простое правило. Резистивные экраны чувствительны к нажатию, а емкостные – к касанию. Эта разница обусловлена конструкцией тача и никак не может быть изменена программно, хоть на просторах интернета мне однажды пытались доказать обратное. Резистивный сенсорный экран – это стеклянная панель с гибкой пластиковой мембраной. На саму панель, как и на мембрану, нанесено резистивное покрытие, а пространство между стеклом и мембраной заполнено микроизоляторами, которые равномерно распределены по экрану и изолируют проводящие поверхности. Если говорить очень грубо и в двух словах, то данный дисплей находится под постоянным током в 5 вольт, а когда на экран нажимают, панель и мембрана замыкаются. Меняется напряжение, и процессор, регистрируя изменение сопротивления, вычисляет координаты нажатия и преобразует его в координаты x, y. Подробнее об этом процессе можете почитать по ссылкам в описании. Вследствие того, что в резистивном тач-экране используются принципы замера изменения сопротивления, а на английском сопротивление это resistance, то сенсоры и назвали резистивными. На них можно нажимать чем угодно – пером, стилусом, ногтем, пальцем, тыкать палкой, он реагирует на все, что его нажимает. Но есть как достоинства, например, можно елозить по экрану вилкой и он будет реагировать, так и недостатки. Например, недолговечность, наличие гибкой мембраны и плохая светопроводимость. Второй тип сенсорных экранов мобильных – емкостный экран. Он реагирует на касание, а в основе принципа его работы лежит замер изменения напряжения на поверхности за счет электропроводности самого человека. По углам емкостного сенсорного экрана расположены электроды, которые подают на экран небольшой переменный ток, образуя сетку. При прикосновении нарушается структура этой сетки за счет того, что тело человека забирает часть тока себе, и в электрическом поле тача образуется утечка в виде точки, потенциал которой меньше, чем потенциал у электродов. Процессору остается лишь снять данные с электродов и вычислить координаты точки касания. Однако такая модель способна распознать всего одно касание. Стало быть, мультитач реализовать здесь не получится. Поэтому для мультитача на обратную сторону экрана и нанесена целая сетка из таких электродов, которую мы и привыкли называть сеткой тача. На некоторых дешевых девайсах она даже видна на солнце. И вот чем больше таких электродов в экране, тем больше одновременных касаний может распознать девайс, и тем точнее отображаются касания. Кстати, такую структуру называют проекционно-емкостными экранами, но для упрощения можно называть их просто емкостными. Отсюда и появляются в характеристиках смартфона данные, например, мультитач на 2, 5 или 10 касаний, и чем больше, тем лучше. И не потому, что я не нажимаю на тач 10 пальцами, а потому что точность у мультитача на 10 касаний будет выше, чем точность мультитача на 5 и тем более на 2 касания. Поэтому девайсы с мультитачем на 2 касания лучше всего не брать, так как, во-первых, в них используется дешевая тач-панель и касания могут просто не распознаваться точно, а во-вторых, очень часто бывает, что находясь на одной плоскости, 2 касания могут работать некорректно или вовсе сливаться в одно. Также у емкостного экрана нет никаких гибких мембран, и за счет этого он может проводить больше света, поэтому яркость подсветки можно снизить, чем сэкономить заряд аккумуляторной батареи. Ну и заключение. Да, за емкостными экранами будущее. Единственный минус – он не способен реагировать на нажатие твердыми предметами, если ваши руки находятся в перчатках. Но это не проблема. Производители на заводе могут выкрутить чувствительность тача на максимум так, что экран будет реагировать и на приближение руки, и на касание в перчатках, а если еще чуть-чуть подкрутить, то даже на стилус и силу мысли. Резистивные экраны – это уже вчерашний день. Емкостные сенсорные экраны превосходят их по всем параметрам. Их уже не нужно постоянно калибровать. Легкие касания заменили нам нервные нажатия, а на смену постоянно теряющимся стилусам пришли пальцы. Хотя у некоторых они тоже теряются, но это совсем уже другая история. Некоторые производители до сих пор выпускают смартфоны или планшеты со стилусами, как, например, линейка Galaxy Note у Samsung, но там используются специальные емкостные стилусы, работающие в паре со смартфоном или планшетом. Однако мне кажется, что все это на любителя. На этом все. Подписывайтесь на канал, чтобы узнать больше об устройстве и принципах работы мобильного железа и всего, что с ним связано. Вступайте в группу ВКонтакте и заглядывайте на второй канал. Конечно же, ставьте оценки этому видео. Пока!
Вы это видели, но есть еще один сам очень...
Что позволило смартфонам стать технологией настолько привычной для нашей жизни, что сегодня нам страшнее потерять...
Есть еще разница, ну, это по-английски есть еще разница, они зависят от воды. Ну, c'est pas ça. Faites défiler, sorry, okay. Whew. No.
Славка, это без звука, да?
Да, я думала, что там был другого фильма, нашла, но очень много получилось и отказалась от этого. Здесь написано, да, но нужно читать. Там были демонстрации, что некоторые, да, уже чувствительность многих таких капацитивных, вы можете и вначале, те, которые были разработаны, не было никакой чувствительности, потому что это от нашего электростатического поля. Нашим электростатическим полем мы управляем. А если у нас перчатки, зависит, какие перчатки, если они из кожи или такие вообще вы не успеете управлять тачскрином, экраном сенсорным. Но там была демонстрация, тоже зависит от воды. Ну, я не того... Ну, ничего, наверное, может, в будущем будут еще лекции, я найду. Но так много могу показать, рассказать, что невозможно в одном, ну, в трех часах. Это очень много. Хотелось показать что-то, но это совсем короткое Internet of Things. Это был принцип этих экранов, и было другое тоже зависимость от воды. Так что I'm not sure you want a finger is electrically conductive. Yeah. Это наше электростатическое поле, которое управляем. And this is the computation where our finger is. This is capacitive, the principle. How they measure where it is done. And with resistive technology, we can't, it is impossible to make multi-touch screen. You can read this, that it could be the computation between the two, but in capacitive technology, you have already multi-touch screen, and this is what in nowadays phones have. I insist that in the most navigation systems, the screens are resistive. The technology is resistive. There were other technologies, infrared. I didn't speak about this because it's not. Here is a good explanation how they track this. Of course, it's not done by touching, it is the software behind. The position is calculated and there is a, okay. So.
Hi, this is Tablet Technologies, and we're going to take a look at the Conquer NX8 tablet with capacitive screen and compare it against the resistive screen version. So traditionally we've sold the Conquer NX.
Okay, trends and device technology. I will end with this. Now I will make a very short presentation of Internet of Things. Did I share correctly?
Yes, yes.
Okay. What exactly is Internet of Things? This is, what is the difference? Maybe you know. Of course, the students know. Internet, before there was just called internet, but it was internet of humans. Internet connecting humans, although it connected computers. Why internet of things? Because this is the, I'm sorry again, sorry. Why internet of things? Because it is connection. What I spoke at the beginning, our experience of my PhD students with ETH Zurich, it was not internet. There was a connection, wireless connection, but it was not through internet. Nowadays, internet is used already to communicate between the sensors. It is mostly sensors with some other devices, and could be sensors and machines even. Smart systems, okay, these new smart systems, intelligent sensors, and something about sensors I want to mention. It's something what engineers should know. Many nowadays they speak about intelligent sensors or about digital sensors. It doesn't exist. The world is analog. Everything around us is analog. The temperature, the speed, everything is analog. Our life is analog. Okay, some physicists don't agree. They say, no, the world is quantum. This is the quantum physics. We don't think on this level. We think on our life. Everything that we measure is analog. So the sensor measures analog values. Of course, it needs analog digital converter because we know that digital with not only calculation, digital treatment of data is more precise, more fast, etc. That's why we need this information in a digital format. That's why the analog digital device converts the data measured by the sensor, and on the output already of the package in which we have a sensor and ADC, analog digital converter, and they call them digital sensor. Okay, but you as engineers, you should understand, or programmers, doesn't matter, as intelligent, technically educated people, you must understand what the question is. Intelligent sensors already, smart sensors, to this system, maybe they add some controller, some other, or system for with displays or something, or for sure there is some calculation, and they show more information than that one measured by the sensor. These are this is in fact what we have. How they call it, this is the people who are not educated, they can think that this is something extremely complicated, but we know what we have behind. So this is the combination, sensors, connectivity. I wouldn't say people and processes, mostly processes. In some cases, what is I was not aware of what they call Industry 4. It is old fashioned now, also Industry 4. In fact, Industry 4, this is the industry automated or robotized, and this is thanks to sensors, connectivity, machines, sensors and actuators we have. So even in microelectronics, in the foundry, because of the need of cleanness, full cleanness of the air and no pollution. If one air is 50 micrometers, 80 is the black, 30 micrometers is the blonde. Can you imagine in the nanometer technology integrated circuit, what damage can we have only from one hair? I don't speak about the dust, etc. And everything is robotized. And we have sensors, we have connectivity, and we have the actuators performing. You saw in the previous movies, you saw some part of these automated foundries. So I can't remove this. It's strange, but I'm trying. Okay, sensors and actuators. What we have, we can measure, and this is part of the Internet of Things. We can measure position, we can measure motion. Of course, I can teach you a lot on the principles, physical principles of the sensors. And they are not only physical, they're chemical. For example, here, when we measure the gases, these sensors are very important in also the liquids, but the contents of what we have. These are very important sensors, and you know that nowadays everywhere we have Internet of Things to control the air pollution in the cities, and not only in the cities. They started with the gases in some enterprises, some power plants, and with chemical sensors, gas sensors, they call them gas sensors. They are based on physical principles. We measure the quantity of the air and usually there is a centralized system that shows these results. This centralized system is the Internet of Things system. We can measure, okay, temperature, you know very well, and there are different principles, and also the humidity, the acoustic, sound, vibration. We can measure force, load, torque, strain, pressure. The leaks, if exists, electric, magnetic, it's something that we also measure it is very important to be measured as well. Acceleration, machine vision. I explained to you about this sensor for glucose measuring. Should be chemical. This is something that I don't know. So GPS sensors, okay. Eye and ears using cameras and microphones. We can measure where the digital nervous, the human body, we are also, our body is, part of our body is a sensor system. The eyes, the ears, that's, we use these principles for the cameras and microphones. And the sensors that for touching that we have, these are also our biological sensors. Hopefully, we still don't digitalize this, don't discretize this information in our body. So, connectivity. So, these inputs from the sensors are digitized by, as I say, analog digital converters and placed into networks. And they are digitized, transferred by antennas, small antennas. We need emitter because the sensor itself, it can't emit anything. It just measures something and output usually some electrical value. We need antenna to transfer this signal, and it depends on the frequency, what we can do of not odd, but of smart applications and smart. Smart is only the human. All the rest is something that the smart humans created. So don't believe in these theories of the artificial intelligence and smart systems. They are smart because we are smart and we could create them, we could program them. So how to transfer? There are different systems. It depends on the frequency. They are, it's different antennas. These are, it could be Wi-Fi, it could be Bluetooth, it could be, but these are different communication possibilities, Ethernet, and usually this is wide area network, metropolitan area network. This is, it is not only for ecology. This is for control of the traffic in the towns. This is for finding a place in a parking. There's such a system. It's a pity that you can't travel. Last year, in a project with Mongolia, we visited a fantastic laboratory at TU Berlin, Technical University of Berlin. Fantastic laboratory, financed, of course, not by the university, but mostly by the automotive industry that is developed very, very well in Germany, you know. And it was a system to control the traffic perfectly. And this system, the Internet of Things, in fact, is the basics of electronic cars. You can't have, in order to use fully automated electronic car, doesn't matter electronic or on essence, but usually it will be on electronic. So you need this system. Otherwise, it is very dangerous. Maybe the automated car can drive in a desert or in big road. But in town, we need this sensoring system, very smart sensoring system. And we could observe on big screens in this laboratory how they control. And of course, with this system, they control the lights to optimize the traffic. But the financing of this research and of the creation of this Internet of Things to control the traffic was, the principle was the future of fully automated cars. You know that in the States, they hurry, they want to be always the first in the world, and they started with some automated cars, but they were victims and they stopped. So different applications. I spoke already about the health applications, but there are much more applications. Okay, smart, what is smart? Let me see what they call smart resources and money. Okay, yeah, we can control the temperature at home, the heating with those. What is more easy, because I studied automation, we can create absolutely independent system, measuring the temperature in rising or taking off some heating. Nowadays, they create it with the use of phones. We receive the information on your phone and you control from a distance. Yeah, it is more flexible. Otherwise, the system could be, if the system is completely automated, it will be fixed at which hour to have heating, at which hour to stop it, etc. But with your phone, you can control not only this, you can control everything at home now. About the cars we spoke about to go, it's automatic cars. It's also health application of sportsmen. The sensors calculating all this. This is not completely new thing, huh? And there is no Internet of Things with these activity trackers, because they are on your body and you follow them. Of course, your trainer can control from a distance. Smart outlets, you can from a distance control your electrical devices at home, etc. Parking sensors, I spoke about the parkings and about the traffic control. Yeah, in the smart city, so-called smart cities, you can see that everything is smart except we. Of course, it is just the opposite. We are the smart. Okay, they say that they saved a lot of time in San Francisco to find, but yeah, this is a big problem. In big cities, it's very difficult to find a parking, for example. And so this is a very good solution as well. So they made this example. It facilitates a lot. Healthcare, I spoke about some applications, and this is a very good example, and they use them for observing the elder people living alone at home. With different sensors, they measure where they are. If they move not, they can measure their pressure, they can measure, sensors. We can have sensors that measuring their pressure, measuring the movement, and if there is some problem, the children or the doctor can act and in urgency help them. This is also very useful. When we worked with ETH Zurich many years ago, when Internet of Things was not yet a term, these kind of sensors were used for the people working on petroleum platforms, because they are in the middle of the sea, the ocean, and there are few people there, and there are not many people to help them. So such systems were used, and if there was some problem, some health problem or some emergency problem, helicopter was sent to help them. You may ask why these systems are not used in Arctic and Antarctic regions. And the big problem is that the sensors are very sensitive to the temperature. And when it's very cold, there are a lot of problems. Not only the sensor, you know, the electronics is very dependent on the temperature. And at so low temperatures, the functioning is not so reliable. The same is in the space, because this project is about space applications, the integrated circuits. There are a lot of research on the specificity of integrated circuits in the space. It's a question of pressure, it's a question of radiation that we have. In Toulouse, in South Toulouse, this institute, they work a lot on microelectronics for space applications. So smart buildings, about controlling the light, controlling the heat, it is also a good application. I want to show you the movie as well. That's why I hurry. So trends in devices. I hope I did trends in devices. I'm not sure. Okay, it's better to share the screen because I will go to the sound. Okay, trends in devices. Oh. Okay, that's okay. Nanoscale to microscale, what we have in nanometers. Nanotools, it's okay. The to continue with the future in ambient intelligence. We call it not artificial, ambient intelligence. These devices that are sensitive and responsible to our presence, etc. More than more, the next expectations. This is what Intel presents to carbon nanotubes. There are a lot of research, since long time. For now, it's okay. They work very well in carbon nanotubes. I want to present you what is the future, maybe, because maybe in 5 years, everything will be completely different from nowadays. Maybe we will not more use silicon. Carbon is very, okay, there are a lot of expectations for it, but until now, the problem is interface. The interface is the problem with the, I wanted to make a presentation on the quantum computers, but quantum computers, okay, they're okay, but the interface is the problem. How to connect these quantum computers to the keyboard, to the mouse, to us, to the humans. So this is the problem. Maybe it will be the future. The carbon nanotubes, they have fantastic characteristics, but we still don't know when the problem with the interface with the packaging will be solved. So what we expect, novel functionality, extending Moore's law in 3D. It already exists in the new transistors, the energy efficient design, etc. Zero power concepts. These are just concepts, not so realistic. With Australian PhD students, I had, we collaborated with them, and this is a little bit, it is more politics than real engineering, what they say. Trends in materials, 3-5 compounds. These are gallium arsenide, what I spoke, different contacts, nanowires, etc. I'll go to the movie with the challenges before. Below 10 nanometers, I want to end with the movie of Taiwanese company that is really the best in this is very important what I show now, because maybe it will not tomorrow, maybe in two years we will have these new technologies. And for programmers, it is the new design methodologies. With these milliards transistors, we need really new approaches to the design of integrated circuits. Okay, this is about the iPhone. They will not speak about our phone, but they will show us. Can you share with sound? Okay. In this Taiwanese company.
Lacroix Group and its ecosystem.
Over 30 years, Taiwan underwent massive industrialization in what has become known as the Taiwan Miracle. Huge tech firms grew, becoming household names: Asus, HTC, Acer.
TSMC.
At the centre of this was the semiconductor industry, led by a company you've probably never heard of, TSMC. It's one of the largest semiconductor manufacturers in the world, producing the chips inside some of the best phones, including the iPhone 11.
It is most likely, if you have a smartphone, you have something made by TSMC.
And these chips were only made possible thanks to the discovery of semiconductors.
Why is semiconductor important or interesting? Because it changes your life.
With factories, or fabs as they are known, across the globe, the largest is here in Taiwan. We've been granted exclusive access to see just how those chips that form the heart of our electronic devices are created. But before we could go into the fab, there was quite a process to undergo. I have to take my shoes off on the carpet, then put them in a locker, it seems. And that was just the start. I had to put on a hairnet, wash my hands, and wear this to keep the dust out. Phew, but it is time for an air shower. Weird, I feel like I'm in the tumble dryer.
The manufacturing of wafers has to be extremely precise. They cannot tolerate any particles that may fall onto the wafer and damage the chips.
So finally we were allowed in the factory, and there was a good reason for all of that faff. The speed of these chips relies on how many transistors you can cram into a tiny space. And when I say tiny, I'm talking nanometers. So even specks of dust would matter.
I don't really know how to describe how fine that 5 nanometer or 7 nanometer is. But I think people very often say, if you look at 28 nanometer, it was like 1/1000th of the diameter of a human hair.
In this fully automated factory, the lights are kept yellow to protect the product, and the machinery is moving all around. But there are quite a few things in here we're not allowed to film, because this is seriously cutting-edge technology, so it needs to remain pretty secret.
We have to protect our customers' information, whichever way we can. And so basically, we do not allow cameras to freely roam inside our fab, is because inevitably they may pick up customer information.
Between all the automated devices in this facility, they travel 400,000 kilometers a day. To put that into context, that's 10 times around Earth. All of this is about the concept of keeping up with Moore's law, as predicted by Intel engineer Gordon Moore in the 60s. It refers to the doubling of transistors on a chip every 2 years, whilst the cost is halved. A concept increasingly hard to keep up with, despite us expecting a lot more from our ever-connected lives.
The next driver is what we call ubiquitous computing. It is computation everywhere at any time. All the devices are connected. Billions and billions of edge devices that are smart, that can compute at any time and communicate and link. And that will be the future enabled by semiconductors.
Okay. So, change, no, just... Вы можете остановить мой экран, потому что...
All chips start out with a very simple raw material, sand. Sand is primarily made up of silicon dioxide or silica. Silica.
Вы остановили? Я не вернусь. I don't want to share the screen. Stop. Okay. Ну, так много еще можно рассказать, и есть связь или нету?
Yes, Professor, you can talk. We are hearing.
Okay, no. I think that, yeah, we spent our 3 hours. I have so many things to tell more and so interesting, but I hope to do it in face-to-face mode, when we meet next time. And I'll show you more and more interesting. If it's, of course, it's interesting for me. I'm not sure it's interesting for you and your students.
No, it was very interesting. Thank you. Thank you very much.
Okay.
And if you are finished, is there any questions, please?
My student. At the same time, I'm connected. That's strange. I'm connected to my. What happens? I was connected to Microsoft Teams, and I heard my student speaking.
Great.
They're also listening, but they are in the French faculty. Okay, good, not bad.
So it was even dissemination, not only within the Uzbekistan. So
Yeah, but the truth is that it was in the other computer, and I didn't know I was with them. Good.
круто, круто.
Хорошо. Ну,
Олег Непомнящий спрашивает опять-таки насчет презентаций.
а я вам пошлю по мейлу?
Да, по имейлу, если мне отправите, и мы поставим его на веб-страницу.
Я отправлю. Мне кажется, что есть, не знаю, в Microsoft Teams я могу там студентам это, но потому что в Zoom, не знаю, есть такая возможность. Я вам пошлю. Сейчас, когда закончим, я пошлю, чтобы не забыла.
Хорошо.
Хорошо.
Спасибо. Спасибо большое.
Спасибо за внимание.
Спасибо всем. И мы сделаем опрос о самой, так сказать, и организации, и вообще questionnaire. Пожалуйста, будьте активны. Это будет и плюс, наверное, для проекта, так как отзывы слушателей все-таки нам нужны. Ну, профессор знает больше. Спасибо большое всем.
Спасибо вам.
Thank you very much. Рахмат хамаге.
Have a nice day and successful year.
Yep. And I think it is lunchtime.
Всем удачи, хорошего дня.
Спасибо.
Rahmat hammaga, sog' bo'linglar.
Sog' bo'linglar.
Rahmat.